Thanks for the introduction, Bob. So I'll start by highlighting that we have working silicon. Here's a system on display at a trade show back in November, running several video analytics demos. On the monitor in the foreground is a quote from Linley. There's an in-depth NPR article that you can read for free by going to our website. While we have working silicon...
Parviz, the slides are scaled a little bit. Is that full screen?
Yes.
Okay, not sure why. They look like they're scaled a little bit.
Can you see the Centaur technology copyright at the bottom? Can you see the entire slide?
Yes, it's just smaller than the available space. So it's fine. Go ahead if there's nothing you can change there.
Okay. Yeah, sorry about that, folks. While we have working silicon and we have audited benchmark results, I want to point out this is not a product announcement. Today's presentation is just about technology. So today's talk will go over a little bit of background, who Centaur Technology is, some of our motivations leading into this project, constraints, the architecture we came up with. I'll go over what our software stack looks like. We'll talk about some benchmark results. And finally, in conclusion, we'll reflect on the design. So who is Centaur? Centaur was co-founded by Glenn Henry and 3 others who left Dell with the idea of making a low-cost x86 processor. We actually celebrate our 25th anniversary this month. Centaur is owned by VIA Technologies, and our entire team is in Austin. We only have about 100 people, but that includes everything needed to produce custom x86 SoCs. That includes architecture, logic design, verification, silicon bring-up, and system test. We've shipped millions of x86 processors with top-tier OEMs like IBM, HP, Dell, Samsung, and Lenovo. So how did this AI coprocessor, which we call Ncore, get started? Centaur was developing a new SoC called CHA, which is going to have brand new x86 cores. This SoC was targeted at the edge and cloud server markets, and we were focusing on high-end x86 features. We saw huge inference markets beyond a hyperscale cloud, IoT, and mobile. For example, we talked to some companies in the video surveillance space. They wanted to provide deep learning-based video analytics to their customers. There's been a lot of focus towards putting inference capabilities in the cameras themselves, but that poses a significant barrier. You don't just have to buy new cameras. We were told it's costly to get technicians to upgrade those cameras and reconfigure them. And these companies are already deploying x86 servers at the edge. All their software ran on x86. However, x86 isn't efficient at inference. These companies wanted to analyze a large number of camera streams with a single system. Today, if you want high-performance inference, you need an external accelerator, probably a GPU. And we would be happy to support GPUs with our SoC. We actually have 44 lanes of PCIe. However, these companies didn't want to add GPUs to their systems. They didn't want to increase the cost or the form factor. So the obvious question to us was, why not integrate a coprocessor to address these workloads? We believe we could integrate an AI coprocessor on the SoC for very little cost. Many of the components we would need to accelerate AI workloads were already going to be on the SoC anyway. There would be no additional NRE for a host processor since we already had x86 cores, the memory hierarchy including the caches and DDR controllers, the I/O, the buses, and the package. In fact, there's often free space on these complex SoCs due to the I/O and pins. Having many high-performance x86 cores to support the coprocessor offers tremendous flexibility. We can choose to offload some of the work to the x86 cores, and we wouldn't have to implement every operation. Since x86 is the de facto platform, deep learning frameworks like TensorFlow and PyTorch provide great support for x86 out of the box. You can also prototype things really quickly. For the customer, if they wanted to buy our new SoC to run x86 workloads, we can provide AI inference capabilities for very little delta cost. The coprocessor approach also had challenges. Since we were getting all these things on the SoC for free, we were going to have to live with the constraints of the rest of the chip. We're going to have to design and integrate this coprocessor with as little impact to the SoC as possible. So we weren't going to change the process, the target clock frequencies, power distribution, or memory controllers. I mentioned there's often some free space or free area because there's effectively a hole in the SoC. However, we had very little control over the aspect ratio of this hole. We had to take whatever area was available, and the area that was available would change throughout the design process. Another challenge was how to integrate this coprocessor with our x86 cores. We had to invent something. A major challenge was, where are we going to get the engineers to build this coprocessor? We're a really small company, and everybody was already busy designing the x86 cores and the rest of the SoC. We needed people for RTL, physical design, verification, and software. I'm jumping ahead a little bit, but to give you an idea, Glenn decided he would do all the RTL himself. He would leverage one really good physical build engineer, and we slowly grew a really small software team internally, about 4 people. Based on our constraints, our original objectives and focus were the following. We decided our target application was edge server inference. These are the video analytics services I mentioned earlier. Another goal was to support applications without retraining. In other words, we wanted to provide a great out-of-the-box experience. We didn't want the user to have to do anything special for us. Our primary metric to focus on would be performance per dollar at the system level. Specifically, we wanted to offer a great value for a system that could perform over 1,000 frames per second for ResNet 50. A secondary objective was low latency. With the accelerator integrated on chip, we believe we could offer very competitive latency for single batch inference. A key internal design metric was MAC efficiency, in other words, MAC utilization. We were going to have a limited number of MACs, so we wanted to make sure we made good use of them. A non-objective was to have the best performance per watt. We know performance per watt is an important metric in this industry, but for these edge server applications, the companies we talked to are more interested in performance and price. So we decided to optimize the coprocessor for higher clock frequency to bring more performance at the cost of energy efficiency. Another non-objective was providing record-breaking performance. We knew the GPUs are offering more performance with each new generation, but we have a modest area budget. We're not going to compete with a device that's 500 or 600 square millimeters, or of course, wafer scale startups. So let's look at what we ended up with. This is the CHA chip structure. I haven't talked much about the x86 cores, but there's 8 of them. They have similar IPC to Intel Haswell, but in addition, we support AVX512 instructions. Note this is a brand new core and has much higher performance than the previous generation of cores that we've designed. We have 16 megabytes of L3. You can see the L3 slices attached to the cores. We have 2 512-bit ring interconnects. Those are the 2 blue rings in the diagram. We have 4 DDR4 controllers and 44 lanes of PCIe. There's also multi-socket support, and the cores in the ring run at 2.5 gigahertz. We decided to attach our coprocessor, Ncore, directly to the 2 rings. It's shown here at the top. That way it could easily communicate with the x86 cores, the L3, and DDR. Here is the final SoC. It's just under 200 square millimeters. It was taped out in TSMC 16 nanometer FFC. To the left, you can see Ncore and its RAMs labeled on the overlay. You can see the 2 ring interconnects in white going through the 8 cores and their L3. You can also see the DDR controllers at the bottom and the I/O and PCI at the top. Let's talk about connectivity. Ncore is the black box in the center and the orange rectangle below it. The coprocessor appears to be a PCI device. It's got 32 megabytes of memory mapped address space. An x86 core can read and write to the coprocessor through our slave interface to the ring. That includes the coprocessor RAMs as well as status and control registers. The coprocessor can also raise an interrupt to demand some action from an x86 core. In addition to the standard AVX512 move instructions that can read and write to the coprocessor, we also added some custom x86 streaming instructions that have higher performance. However, our most important connectivity for performance is our DMA engines. We have 2 DMA engines that can talk to other devices on the ring, notably the DDR controllers in the L3. The coprocessor initiates the DMA transfers. We can have up to 16 outstanding transfers, and we use barrier instructions to synchronize the coprocessor with the completion of specific DMA transfers. So what is the basic architecture for Ncore? We had to come up with some architecture that was based on our constraints. Remember, we weren't sure how much area we would really have. We needed a design that would easily scale to fit whatever aspect ratio we were given at any moment. Rather than a systolic array, the requirement to be flexible in our physical design led us to develop a SIMD architecture organized into vertical slices. Centaur has a lot of experience making SIMD designs area efficient while still reaching high frequencies. More importantly, the SIMD approach is generally much more programmable, and we wanted the flexibility to easily add new operations to support new workloads. Ultimately, we wanted to run as fast as possible, but not faster than the cores. This is the physical organization of the coprocessor. There are 16 slices, each 256 bytes wide, totaling 4,096 bytes. To put that in perspective, that's 64 times wider than AVX 512. You could call it AVX 32768. Remember, this is a simple programming model, one core with a really wide SIMD unit. Notice the horizontal area became available, we could add more slices. These are the vertical slices, the white box in the diagram. And as vertical space became available, we could add more SRAM. You can see the logic and the RAM labeled in the top leftmost slice. This is all running at 2.5 gigahertz, which results in 20 teraops per second of peak compute. Each RAM has 2,048 rows, where each row is 4,096 bytes. And we have 2 of these RAMs, so we have a total of 16 megabytes of SRAM. Note that's in addition to the 16 megabytes of L3. All right, let's push deeper into the architecture. You can see the pipeline on the left and the instruction sequencer on the top right. So one instruction controls the entire pipeline. The instructions are 120-bit wide. They're very low level. They're like microcode. All instructions execute in one clock. That includes 0 clock branches, loops, calls, and returns. The instructions also control the 2 DMA engines I mentioned earlier. The NDU, the neural data unit, is attached to the side slice of other NDUs such that it can rotate an entire 4,000 byte row in one clock. The NDU functions have 8 possible inputs and 4 output registers. Remember, this is all 4,000 bytes wide. The NDU performs 3 parallel operations. It could be passing an input to an output register. It could be compressing a block, which is like a byte gather operation. It could be rotating an entire row by powers of 2 up to 64 bytes. You can broadcast bytes. You can do funny things like edge swap, used by some of our algorithms that effectively swap bytes at a certain stride. We can merge input with the NDU output registers using another NDU register as a byte mask. And remember, all these functions execute in one clock. Moving down the pipe, the next unit is the NPU, or the Neural Processing Unit. The NPU supports 9-bit and 16-bit integer, as well as bfloat 16. We decided to add support for bfloat 16 since some workloads have issues with quantization, whether it's accuracy loss or just issues with tooling. A 9-bit integer MAC takes 1 clock, and a bfloat 16 MAC takes 3 clocks. The NPU does other functions like add, subtract, min, max, logical operations, and variations on those. Each NPU has 8 predication registers, and every instruction can conditionally write to the accumulator based on one of those predication registers. We have a saturating 32-bit accumulator. In integer mode, it's a 32-bit integer accumulator. In bfloat 16 mode, it's a single precision floating point accumulator. The inputs come from the NDU registers above, and they're forwarded to the NPU inputs. Note I said the NPU supports 9-bit operands rather than just 8-bit. That makes it easy to support asymmetric quantization where you need to subtract an 8-bit offset and you end up with a 9-bit operand. Moving down to the final stage, the out unit. The out unit performs quantization of the 32-bit accumulator back down to an 8-bit or a 16-bit or even a bfloat 16 value. It supports the quantization schemes that are popular in TensorFlow and PyTorch. It also does ReLU, tanh, and sigmoid. Results go into 2 out registers. These can be stored directly to RAM or forwarded to the NDU as input. The full 32-bit accumulator can also be stored directly to RAM in a couple different byte configurations we call horizontal and vertical. All functions execute in 1 or 3 clocks, but some functions are pipelined in mux to 8 to 1. This results in a worst case of 10 clocks. However, these outs are relatively rare since they only happen when we complete a dot product. Since we're typically accumulating really long dot products, we just latch the accumulator so they can start the next dot product without being stalled. If we exclude the RAMs, we are 11 square millimeters. That's 1.3 million registers and about 20 million gates. So let's talk about the instructions. They are 120 bits each. They're broken down into various fields that control different parts of the pipeline. For instance, a single instruction could have the following encoding: 30 bits of control for the 2 RAMs, 22 bits for branching, 20 bits for control of the NPU for different arithmetic, 15 bits of control for the NDU's ability to write to RAM, 26 bits of control for the NDU's other functionality, and 15 bits of miscellaneous control. These instructions are fairly low level, and we don't plan to make them public because they're not going to last for more than 1 hardware generation. With that said, we think programmability is really important, and we want users to be able to leverage our heterogeneous platform, and we're working on tooling to support that. However, today I'm going to focus on our current software stack. So here's our software stack. Our core libraries are all framework independent, so it's just a matter of integration for various frameworks. Here we're showing TF-Lite. TF-Lite is unique that it offers a dedicated interface called the delegate interface for accelerators to plug into. What that means for the user is that if they have a TF-Lite application, they can leverage our accelerator with about 3 additional lines of code. The TF-Lite flat buffer at the top is just a standard TF-Lite workload. It's presented to the TF-Lite interpreter, which through the delegate interface negotiates which parts of the workload should go to the coprocessor instead of the x86 cores. Ultimately, a partitioned subgraph is presented to our graph compiler, the GCL, which first does some of the graph level optimization passes. For instance, merging pad operations into an adjacent convolution. It also does an analysis pass to determine the optimal buffer layout for each operation. The graph compiler will leverage our Ncore kernel library, the NKL, to turn the entire subgraph into a single binary called a loadable. This loadable can now be executed by our runtime library, which is code that runs on an x86 core and manages the execution of the coprocessor. Note our software stack also includes optimized x86 implementations for some operations, in particular to leverage AVX512. I'm happy to say we have benchmark results for the MLPerf Inference 0.5. There are so many companies in space, and some of them are just quoting theoretical peak compute or other contrived benchmarks, so I think it's really important to have this benchmark suite. The submission was due last October, and we only had working silicon for about a month, but we're still able to submit most of our benchmarks. This is a subset of the submissions. Our results in the left column, and I want to point out that we submitted as a preview system while the other submissions on this are available, with the exception of the Intel on the far right. Let's talk about latency. This is the single batch inference scenario. We have the lowest mobile net latency of any submission that includes a lot of expensive hardware. The NVIDIA Xavier is a complex SoC targeted specifically at deep learning applications. For ResNet 50, our submission had half the latency of Xavier. I also want to point out the dual socket Intel server submission. This beast has 112 cores, the latest AVX512 v9 instructions, and yet we provided similar or better latency across the board. Now let's talk about throughput. In this mode, you can configure your system to use as large batches as you want. We actually still use the batch size of 1. I want to point our SSD submission had an issue, had a software bottleneck. We've fixed that and bumped the score up from 652 to 2000 frames a second. So on the far right is an Intel submission with 2 of the 10 nanometer inference, Nirvana inference cards. So while they're 5,000 frames per second each, you still have to buy your server SoC in addition to these cards. We mentioned earlier that we wanted to hit 1,000 frames a second for ResNet 50. In this submission, we achieved 1,218 frames per second. On MobileNet and SSD, we're competitive with NVIDIA Xavier. Remember, it has 8 large ARM cores, large GPU, and 2 deep learning accelerators integrated on the SoC. So what do we make of these results? Remember at the beginning of the talk I mentioned x86 wasn't efficient at inference? Let's focus on Intel server submission for throughput. The Intel server submission has 112 cores, 154 megabytes of L3, and 24 memory channels. Plus, each of these cores have 2 AVX512 units and the new VNI instructions. For ResNet 50, if we take their score and normalize it per processor, you get 53 frames per second per core. Our coprocessor is equivalent to 24 of these cores, which are effectively the world's best x86 cores. It's important to note that in our benchmarks, most of our x86 cores are idle. Since we aren't doing any heavy computation on our x86 cores, they're free to run normal x86 server workloads. If you look at our MobileNet scores, you'll see the same thing. We think we're offering a tremendous value with a coprocessor instead of relying on x86 alone. So our conclusions, a very small team can do a lot. Centaur has proven this over and over for the last 25 years. We think a coprocessor approach is the way to go. Minimizes cost, you can offload ops to the CPUs. A 32,000 bit wide SIMD approach actually works really well. We had a lot of doubters, but our results are pretty strong. Our original architecture and guesses actually worked out pretty well. Our utilization is pretty good. Now that we have running applications, the design is probably not as efficient as it could be in retrospect. The RAM subsystem is slightly overkill and not optimally shaped. A few additional sequencer or NDU functions would help performance. Different slice geometry probably better, and ultimately, we believe we could stuff more performance in the same area. That's my talk.
The first question, and there's Glenn. First question from an attendee is, what is the TDP range you're targeting with this processor?
Glenn, do you want to comment on that?
Well, since we're not a product, we're not quoting the power numbers now, but I would say that it's the TDP is somewhere between 10 to 100 watts. It's in that neighborhood. It's similar to the power of an 8-core x86.
Okay, so I think we're talking about something that would be in the realm of a Xeon D type product. Is that what sort of you would see as the competition here?
Yes.
Okay, thank you. Next question from the audience is regarding the hole for which you filled with the Ncore. It was fairly large, was the observation. You really didn't have to grow the die to add the Ncore and its associated memory?
Not really. The hole started quite small, but I was counting on the fact that history says that things get bigger, not smaller. So as the rest of the SoC grew, things got bigger. And there's a lot of pins with the 44 lanes of PCI and the 4 memory controllers. So we might have made the die a touch bigger, but not really.
Okay, thanks, Glenn. I have a question, and I see kind of a related audience question here. So can you give us kind of the highlights of your x86 CPU with AVX512? And then the related audience question is regarding any plans to kind of go beyond this Haswell class CPU?
I'll answer the last question first. It's obvious we plan to go beyond both in the x86 core and in the AI stuff. We've been in business 25 years, which means that we have to keep going beyond whatever we built last year. So we're obviously not going to talk about that, but work is well underway on the next generation of parts from us. In terms of the x86 cores, it's about the same, gets about the same performance as a Haswell core, except some applications take advantage of the AVX512, which Haswell doesn't have, which we have. And of course, we have a lot of PCI lanes, 4 memory controllers, so applications that utilize that to get very good performance. But in general, we categorize it as an 8-core Haswell level of performance.
Okay. And regarding the x86 streaming instructions, so those are instruction extensions. Are those only needed in the runtime library, so customers don't have to worry about compiler support? Do I have that right?
Correct. I believe right, Glenn?
Yeah, customers don't need to see those at all. They can use them, but they're there to speed up moving data to and from a core, to and from Ncore, which is primarily done by our device driver. But a user can use them if they want to. But you can also use just plain old AVX move instructions too.
Okay. I guess what was the rationale behind adding those streaming instructions? It was just a question of efficiency?
They're a little bit faster because they one instruction, they're stream instructions like move S. So they one instruction will move a lot of data as opposed to having lots of AVX move instructions, moving a block of data per instruction. A little bit faster, but to some degree it wasn't hard to do, and so we just did it.
Got it. Thank you. An audience question regarding SIMD compiler support on the, I believe this is on the Ncore side. And the question is, can customers compile their own software and get high utilization out of the hardware?
So today we don't expose the ability to compile custom kernels, but we're actively working on that. We're putting a lot of effort in building a compiler stack leveraging MLIR. So we're building a lot of custom tooling, and we do want to enable that for customers to be able to write custom kernels. Okay,
great. And I have one final question here regarding DRAM bandwidth. I'm wondering whether at some point you see with larger models the DRAM bandwidth becoming a bottleneck.
So it's not necessarily a function of model size as much as arithmetic intensity. It depends what kind of workload we're talking about. With most vision models, there's enough arithmetic intensity such that we can fuse kernels and we can stream it to where it's not an issue. If you need to do something like I'll just give an example, some model with a lot of vector matrix multiplications, those simply do not have the arithmetic intensity to stream efficiently, so then we're forced to batch. But even in those cases where we have DRAM bottlenecks, we'll just batch to get our performance up.
Got it. Okay, thank you.